welcome to this video on energy. Specifically, we're going to be talking about open systems today and how we can do calculations with them. When we originally defined systems in terms of energy, we talked about an open system where the total amount of energy is changing, and a closed system where the total amount of energy is constant. And we said that in a closed system, delta E is 0, or in other words, E initial equals E final. And we did math with them, we did problems with them, we solved that out. And that's useful. That's done. We're largely moving past that, so we can start talking about open systems where there is a net force acting on the system, or there's work being done on the system and the amount of energy is changing. The most emblematic representation of this is a car coming to a stop. In the beginning, if we look at the car-Earth system, the car has kinetic energy. It's moving along. We can tell by the speed lines. It has some amount of kinetic energy. We'll represent that with a bar graph. And work is done on the system via the friction in the tires and interaction with the pavement to remove energy from the system, leaving you with no energy when all is said and done. This work done on the system changes the energy, and we can get a little more explicit than that. The work energy theorem states that the amount of work done on a system is equal to the change in mechanical energy, or in other words, work equals delta E. Because multiple forces might be doing work, you might occasionally see a sigma saying the sum of all work, or all the work, the total work done on the system equals your change in energy, delta E. Now this could be work 1 plus work 2 plus work 3 dot 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 equals delta E, which, remember, delta is always final minus initial. But when we focus on only a single force doing work, which is what we're going to be doing for most of today, the easiest way to put this is the force times the distance the force acts for times the cosine of the angle between the force and the distance or displacement it's traveling equals E final minus E initial. So in this case, the amount of work done by friction will equal the change in energy from the kinetic energy. In this case, we know the amount of work will be negative because we have energy, we have no energy. Let's take a look at an example. So in this case, we have a block of 7 kilograms, a box, whatever you want to think about it, and we're pushing on it with an applied force of 30 newtons across a frictionless surface. The reason we're saying frictionless is so we don't have to talk about the work done by friction yet. In the beginning, there is no velocity. Your initial velocity here is 0. And I want to know how fast it's going at the end. Now, previously this would be a hard problem to do because there's a net force acting on the system. But now that we have the work energy theorem, we can take a look at this. So we'll start by, our LOL diagram, graphic organizer. We're looking at the block Earth system. We could just look at the block system because there's no change in elevation, so the effect of the Earth doesn't particularly matter. But in this instant, I'm just going to label block Earth. In the beginning, there's no energy. There's no springs, there's no gravity, there's no velocity, so there's no energy to start. But after we push on it for this 12 meters, there's going to be some amount of EK. It's going to be moving. So we are adding energy to the system. From here, it's just a matter of getting our work energy theorem together. Work equals delta E, or my change in energy. In this case, my amount of work is force times the distance times cosine of the angle between them equals E final minus E initial. Now my E initial is 0. I see this from my diagram, so I can just make that 0 or cross it out. I'm going to leave it as 0 for now. The only type of energy I have at the end is E final is EK, so that's going to be 1/2 mv squared. My angle between the force and the displacement, while I'm heading to the right, my displacement's to the right, my force is to the right. They're heading in the same direction, so the angle there is going to be 0. The displacement is 12 meters. That's how far it goes, and the force is 30 newtons. So at this point, all I need to do is solve for my velocity. In fact, I even know my mass, so I can plug that in really quick. That is the 7 kilograms here. At this point, all I need to do is solve for v. 30 times 12 is 360. Cosine of 0 is 1, so 360 times 1 is equals 1/2 times 7, which is 3.5. V squared minus 0, anything minus 0 is still that same number. Divide the 3.5 to the other side, I get v squared equals 102.86. Take the square root to get the v by itself, and I get the final v over here is 10.14 meters per second. And that's it. That's all we're doing. Instead of knowing the initial energy and the final energy and balancing that out, we're just looking at the amount of work done on the system and using that to calculate an unknown. The process hasn't changed. I have my graphic organizer, I've identified my givens, I've identified my unknown, which is the v final. I use my equation, I substitute in other equations and numbers, and then I solve. The process is still unchanged, it's just how we are going about it. With that said, let's take a look at a practice problem for you. One to try on your own. Talk about a stopping car again. You're driving down the highway at 30 meters per second, which is about 67 miles per hour, and you need to stop, slam on the brakes. Maybe you spot a red light, maybe you spot a cop up ahead, or an accident. Regardless of what you need to do, you need to stop. So you slam on the brakes, you take your foot off the gas, you continue traveling forward as you step on the brakes. What I want to know is how far do you travel before you stop? Now, we could do this as a kinematics problem, but let's do it as an energy problem this time. First thing you need to know the force of friction that is causing you to stop. We're going to use the mu s here because when a car stops, it isn't skidding. If it starts skidding, that's when you'd use the mu k. But if it's rolling to a stop, which is how most cars work, it's going to be that mu s value. So you'll need to draw a free body diagram. You'll need to find the force friction. Fairly simple, straightforward stuff. Once you have that force friction, you can then go through the work problem and solve for how far do you travel, the displacement of your car before you stop. Go ahead, give it a try, check back after the pause. Okay, here we have our answer. The first thing I did is I looked and I drew my graphic organizer. I have EK in the beginning, I don't have EK afterwards, so my change in energy is leaving the system. Helps me visualize what's going on, understand it. Then I need to set up my work equation. Work equals my change in energy, so that'll be my force, which is friction in this case, times the displacement times cosine of the angle between them equals E final minus E initial. The reason I didn't care about my normal force and my gravitational force for my free body diagram is they're both at a right angle to the direction of travel. They won't do any work. They're not relevant. They're not impactful. Force friction is mu times Fn. I need to find Fn. I can do my sum of all forces in the y direction, which is 0, will be Fn minus Fg, which tells me my force normal will equal my force gravity in this case, since I'm on level ground, which tells me that my force friction is going to be mu times force gravity, or mg, mu mg, which is what I got here. Plug that in for my force friction. D is still my displacement. It's what I'm looking for. Cosine of the angle, the car is going to be moving to the right, but friction's acting to the left. So the angle between them is 180 degrees. That's where my 180 comes from. My E final is 0. I got that from my little drawing, or my understanding of what's going on. My E initial is kinetic energy, which has the expression of 1/2 mv squared. If I want to solve symbolically, I simplify over here, masses cancel out, and I get D equals negative V squared over 2 times mu times G times cosine of my angle. Because the angle is 180, they'll make negative and negative make a positive. Cancel out, give me the 51.02. If I solve it numerically, 0.9 is my mu, 650 is my mass, 9.8 is G, D is D because I'm solving for that, it's my unknown. Cosine of 180 is negative 1. 0 is still my initial, but 1/2 times my mass of 650 times my initial velocity of 30 squared. Simplify my numbers, I get negative 5,733 times D equals negative 292,500. Divide to the other side, and I get 51.02 meters. Units would be different throughout, not just unitless, but simplification as we go. If that makes sense, if you did awesome with that, go ahead and give the homework a try. If it doesn't, please ask questions, go over it again. Anyways, thanks for watching.